Really what we're trying to do is understand, in terms of engineering principles, how living systems work, how genes regulate function of cells and tissues and organisms, how the proteins operate, how organisms decide how to respond to stimuli in their environment, and not only understand biology, but then to harness it, manipulate it. Can we use biological components to build better materials, materials that are safer for the environment, drugs that are safer, drugs that are cheaper, drugs that are more effective? Instead of using things that we knew about physics and chemistry over the last century, can we now use things that we know about biology that we've learned the last 10 or 20 years? What we're ultimately after is the design of better anti-cancer drugs, breast cancer in this particular case. What Lisa's working on is some genetic problems that would go wrong in breast cancer. How do they lead to aberrant movement of breast cells into places that they're not supposed to be, tumor invasion, metastasis? What is responsible for that at an underlying molecular level, and therefore how could you intervene at that level with a more effective drug? These are cells that we can grow in the laboratory, and then we're interested in their migration behavior, and are they migrating normally or are they migrating more aggressively than they should be? Because there can be a problem in one of the key molecular regulators or switches that when there's too much of it, you have extra gene copies, or it's hyperactive, that the cells essentially turn themselves on and stimulate themselves to proliferate and migrate, whereas normal cells need to wait for that switch to be turned on by some other appropriate signal. In the movie, what you're seeing are human breast tumor cells under the microscope. We're measuring how fast they're moving, what direction they're moving in. Are they moving erratically? Because the characteristic of a tumor cell might be it moves much faster than it should and much more erratically than it should, so that it ends up in the wrong places. So what we're trying to do is find a way for them to disregard their self-produced signal and therefore only listen to signals that are appropriate from the tissue around them. In terms of how this is progressing, we have collaborations, for instance, with a number of pharmaceutical companies who are even now using some of the results of what we're doing to improve drugs in their pipeline, to design their clinical trials better. That's one thing that MIT is all about, is taking what we're studying in the laboratory and connecting it to real societal problems, whether they're today's problems or problems that can be solved 10 years from now. In this particular case, we're very excited about the fact that we are working with some pharmaceutical companies, and what we are doing in the laboratory is helping guide the decisions they make about what drugs they think will be effective. Biology is complex, and they're realizing that what we're learning about it as engineers is really helping them sort out some of the problems that they're encountering in drug design and development.